This video we are going to learn about series and parallel circuits, or we call it as series and parallel connections. Series and parallel connection. So in these electric circuits, especially in this electric circuits, it is either AC or DC, whatever it is. So we are going to see lots of combinations of connections in the circuits. Either it may be a series connection or parallel connection. So we are going to make that circuit to be simple to find the current through the resistors or current through the elements, electrical elements, whatever it is, resistor, inductor, capacitor, like this. So that type of different combinations of connections are connected by the RLC electrical elements. We have to find out. We are going to make the circuit a simple equivalent circuit. For that, we must and should we have to reduce a complex circuit into a simple equivalent element circuit, like resistance, equivalent resistance, equivalent inductance, equivalent capacitance. For that sake, we are going to learn about this series and parallel connection. Okay. Now, in this video, we are going to learn about the series connection. Series circuit or voltage divide voltage divider circuit. Why we call this voltage divider circuit? Let us see in this video why we call this series circuit as a voltage divider circuit. Let us draw the circuit for the series. See here, let us take three resistors. R1, R2, R3 and so on Rn. So we are going to take these resistors as R1, R2, R3 and so on Rn are the resistors. We are connected in series. This type of connection is known as series. Let us take two terminals. Let the two terminals be 1, 2, 3, 4 like this. See, the second terminal of the first element is connected to the first terminal of the first element. Understand? The second terminal of the first element is connected to the first terminal of the second element, like this alternately. If you take the signs plus, minus, plus, minus, plus, minus and so on, plus, minus. So, the first element negative terminal is connected to the positive terminal of the another element. Simultaneously, it is connected like this. This type of connection is known as series connection. Whatever may be the element. For example, we are taking the resistor as an element here. You can take any of the element. You can take inductor, you can take capacitor, whatever it is. Okay. Now, the voltage source Vs is applied here. In the previous videos, we will discuss about the Kirchhoff's current law and Kirchhoff's voltage law. Those laws are naturally related with the series and parallel connections. So, according to the Ohm's law, how can we write the voltage equations for this? So, we know that if a current I is flowing through it, what happened? This resistance R1 has a voltage drop, the resistance R2 has a voltage drop, resistance R3 has a voltage drop. Understand? So, before going to know this, you are going to know two more things. In a series circuit, current is always same. Series, parallel. There are two type of connections are there, series and parallel. In series connection, current is same in any element. Current through any element is same. Current is same. While coming to the parallel, voltage is same. Voltage is same. While coming to the series connection, current is same in any element. Current is same through any element. Suppose if you are considering current I in this first resistor, in the second resistor also current is same I. In the third resistor also current is same I. In the nth resistor also current is same I. So the current is same through all the elements present in the series connection. Okay. Now see what happened according to this. The voltage across the I into R1, we know the Ohm's law. What is Ohm's law? Ohm's law. So if you want to write the voltage equation, V is equals to IR. If you want to current equation, I is equals to V by R. These are the only two things. If you want to write an equation in voltage, you can write either IR or V when it is a Kirchhoff's voltage law. If you are applying Kirchhoff's voltage law, the equation should be in two forms. Either it should be in I into R or it should be in V or in both. If you want to write the equation in KCL, then you have the equation should have two forms. One is V by R, another one is I. Only in these two forms, if you apply KCL, the equation should be containing these two formats. Is it right? Now see here. Now what happened? V1, V2, V3 and so on Vn. So we are going to find out the equivalent resistance of a series connected circuit. This is a series connected circuit. You are going to find out the equivalent resistance of the series connected circuit. For that we are all doing this. We are going to find out the equivalent resistance equation when the resistors are connected in series. So we are going to find out R equation. Before that, this one is very important. In a series connection, current is same. In a parallel connection, voltage is same. You have to clearly remember these 2 points. Now coming here, what happened? See, R1, R2, R3 and so on, Rn are the resistors connected in series. We know that. Right, apply KVL. Apply KVL for the above circuit. Apply KVL for the above circuit. Then what should you have? Vs equal to what is the voltage drop across resistor R1? V1 plus V2 plus V3 plus and so on plus Vn. Let it be equation 1. Let it be equation 1. So Vs equal to, so what is this V1? Already we discussed in the previous video. V1 is equals to I into R1. I into R1. We know that from Ohm's law. V1 is equals to I into R1. Write that. I into R1 plus I into R2 plus I into R3 plus and so on plus I into Rn. Why? Because this is the voltage drop at the resistor across the resistor Rn. Okay. Now see in each and every term, which is constant here. So Vs equal to, you can write I into R equivalent. You can write I into R equivalent. Then it is equals to I into R1 plus I into R2 plus I into R3 and so on plus I into Rn. Let it be equation number, this one be equation number 2, this one be equation number 3. Now take the common terms here. I into R equivalent is equals to, if you take term common, if you take term I common from this, R1 plus R2 plus R3 plus and so on plus Rn. Let it be equation number 4. From this I gets cancelled. From this I gets cancelled. We can consider here Vs equal to I into R equivalent. Let it be a side. We can use this later. Now what happened? R equivalent is equals to R1 plus R2 plus R3 plus and so on plus Rn. Equation number 5, and this is the equation for the equivalent resistance when the resistors are connected in series connection. What does this equation shows to us? If the elements are connected in series, if the elements are connected in series, that too the element is a resistor, not for inductor and capacitor, not everything. It is a resistor. If you connected a resistor in series, then the equation, the expression for the equivalent resistance, this R equivalent stands for the equivalent resistance, is equals to R1 plus R2 plus R3 plus and so on plus Rn. You can directly sum all the resistors connected in the circuit when it is in series only, not parallel. If it is a series connected resistive circuit, then the equation should be like this. Okay. So, see here what happened if this voltage is divided here. Is it right? V1, V2, V3. That means Vs is divided into V1 plus V2 plus V3 plus and so on plus Vn. So, this applied voltage source is divided into V1, V2, V3, Vn. That means what? It divides the voltage. That's why we call this as a voltage divider circuit. Voltage. Okay. So, this is the V1 plus V2 plus V3 and so on Vn voltage divided circuit. This is all about the series connected circuit. Thanks for watching.